Hi class, this is Ms. Frazita. We're looking at Chapter 3, Section 3 today. So looking at our section title, Dividing Polynomials, we're going to go through a review of how to do it with long division and then also learn how to do what's called synthetic division. So as the title suggests, we're dividing today. So looking at it here, our first example, we have this polynomial. It looks like 3 terms, so we call it a trinomial, and it's being divided by a binomial, x minus 3. So we're going to review how to do this with long division. I assume it is review that you've seen it in Algebra 1, but we'll go ahead and try it. So here's our trinomial. First thing to realize though is that if you're looking at the powers of x, x to the first power is missing here. There's it goes straight from x squared down to the constant term. So when we're dividing, we do want to put in the placeholder 0x to the first. Now the divisor, x minus 3, is going to go out in front. And when I'm trying to figure out what to put up top, I'm just looking at this x here, and I'm just looking at this highest power of x here. And I'm thinking in my head, what can I multiply this by to get this? So x times 2x squared would give me this. So 2x squared is what I put up on top. Once I figure that out, then I'm going to take 2x squared and I'm going to multiply it not only by x, but also by this constant 3. So when I do that, of course I'm getting 2x cubed here because that was the whole point, right? I was figuring out what I needed to put on top in order to get 2x cubed. But when I multiply it by the 3, I get a minus 6x squared. Now, just like usual with regular division of numbers, we're going to subtract. Now, the first term should drop out. Okay, if it doesn't, you did something wrong. The second term, 4x squared minus a negative means adding 6x squared. That gives me 10x squared. I go ahead and bring down the next term, 0x. I think to myself again, just this first term, the variable here, x, what do I multiply x by to get 10x squared? And it would be 10x to the first. So I put that up top, 10x to the first, and again I multiply it to both of these terms here in the divisor. So 10x times x is 10x squared, and 10x times negative 3 is negative 30x. And again I subtract. So this minus this should go away, and I have 0 minus negative 30x is 30x. I bring down the 5. I'm going to do it one more time. So here the 30 times x gives me 30x. So I also do 30 times 3, giving me negative 90. Again, subtracting, and when I do that, these first terms better drop out, and I have 5 minus a negative 90. So 5 plus 90 is 95. Now at that point there's no more terms to bring down, so I have just 95 as my remainder. Okay, so the idea is if there is a remainder other than 0, then we know that it didn't divide into it evenly. If you're going through this long division and you happen to get a remainder as 0, then that means that x minus 3 actually is one of the factors of what you were dividing. Okay, so what we did was long division for this trinomial divided by this binomial. This is what we got. I say plus, and the remainder was 95, so when I write it out, I would put 95 over the divisor, x minus 3. Okay, a couple questions here to reflect on. It says, when you perform long division of polynomials, why must the degree of the remainder be less than the degree of the divisor? Well, that's how you know that you're done with your dividing. So again, when I go through here, if this was still 95x, something like that, and the degree was a 1, and here I'm dividing by something with a degree of 1, I would know I need to just divide one more time, put one more number up on top. So again, the degree of this remainder should always be less than the degree of the divisor. That's how you know that you've finished. Okay, and the second part there, is the set of polynomials closed under division, why or why not? And the answer is no. So here I had a polynomial divided by a polynomial, and what I got was not a polynomial because here I have a fraction with my variable in the denominator. So I didn't get a polynomial. Remember, a polynomial means that each term, the degree has to be a nice whole number. I can't have negative powers of my variable. That's not considered a polynomial. Okay. So moving on, they have the remainder theorem. So it says when you go ahead and do this division, you got 95, and if you evaluate the polynomial at x equals 3, again here I was dividing by x minus 3, so the 0 of that factor would be 3. So if I go ahead and plug 3 in for x, I'm going to get 95, which was my remainder. So this is called the remainder theorem. So if I'm dividing by x minus a, the remainder is going to be what I get if I were to plug that a value in for x in my polynomial. Kind of interesting. Okay, so it says you can use the remainder theorem to evaluate polynomials. So to find p of a, you divide the polynomial p of x by x minus a and find the remainder. Okay, a shorthand method for dividing a polynomial is called synthetic division. Okay, so there's this process here, and it's off to the side. This is what it looks like. So here's our practice one we're going to do. So 2x cubed plus 4x squared plus 5, and we're dividing it by x minus 3. So up here you can see it written with the division symbol and the x minus 3. So first thing to do is think, okay, x minus 3, what is the 0 of that? That would be just 3. So I'm going to put 3 in this little box on the side, or this little corner here. And then I look at my polynomial that I'm trying to divide. And I'm going to pull just the coefficients. So there's a 2 and a 4. Remember, x to the first, we put a 0 as the placeholder, and then the 5. Okay, so here's the process. I've got the 2, 4, 0, 5. I've got the 3. What I do is I bring the 2 straight down. I write it down here. I'm going to multiply 3 times 2. I get 6. I'm going to write it here. I'm going to add 4 and 6 goes to 10. I multiply again. 3 times 10 is 30. And I add straight down. I multiply again. Goes here. I add straight down. So it's always, you bring your first number down just as your first step. And it's always multiply, put it here. Add, put it there. Multiply, put it here. Add, put it there. Multiply, put it here. Add, put it there. That is called synthetic division. So what you get at the bottom, the 2, 10, and 30, those are going to be your coefficients of your dividend, and the 95 is your remainder. So if I were to write it out, do they actually? Yes, they do right here. So if I were to actually write it out, this divided by this is equal to 2x squared plus 10x plus 30 with a remainder of 95. Okay, now when you're writing the actual value that you get after you do the dividing, the 2, 10, 30, you want to make sure that you get your x powers in there in a descending order. Since it originally started with an x to the third power, I always drop it by 1 power because I'm dividing it by x to the first power. So if I have x cubed and I divide it by x to the first, I should get x squared. So my first term, when I have the 2 there, I make sure it's 2x squared, and then the powers of x are just descending. So then it'll be x to the first, then no x at the end. Okay. So here they say we have p of x divided by x minus a, and it'll equal q of x with the remainder over x minus a. Says, where are we? It's the first step in the proof of the remainder theorem. So complete the proof. It's pretty much what we're doing. So here we have this divided by this is equal to this plus the remainder over the divisor. That's what we ended up getting. We're trying to prove this. So what they do is go ahead and multiply both sides of the equation by x minus a to clear out the denominator. So if I multiply this side, these are going to cancel, giving me just p of x. When I multiply the right half of the equation, this last term, the x minus a's cancel, giving you just the r on the end. But I'm going to have q of x times x minus a for the first term there. So at that point, then, we go ahead and say, well, we're going to substitute a in for x. So if I go ahead and plug a in, now I have p of a minus a, q of a plus r. And a minus a is nothing. And so the 0 times anything is 0, and I have p of a is equal to r. So what we've basically just proven is that for our division here, if I'm plugging a in for my polynomial, what I will get is my remainder. Okay, so this actually kind of goes with, if I scroll back up here, I think I scrolled too far. Where was it? Here, this part at the top, that when you plugged the 3 in, you get 95. This is what they were trying to prove, the remainder theorem. Okay. All right, so we're going to do one more example just to make sure this whole synthetic process is making sense. So here I have a cubic. I pull the coefficients 3, 14, minus 1, and 20. Make sure it is a -1 there. Don't forget your minus sign. We're dividing it by x plus 5. So remember, the factor is x plus 5. The root of that factor is -5, the thing that you need to plug in for x to make it 0. So that's -5. So we put the -5 in the box. I bring the 3 down. I multiply. I add. I multiply, I get 5. Add, I get 4. Multiply, -20. Add, I get 0. Okay, so the remainder was 0. That tells you that x plus 5 divided into it evenly. It was a factor of the cubic. Okay, so the quotient, the 3 minus 1, 4, again, are the coefficients 3 minus 1, 4. We had started with a cubic, so we drop it by 1 degree. I get x squared, so I know it's going to be 3x squared, and then x to the first, and then no x. Okay, what is the remainder in this example? Well, it was 0, and how do you know? Well, it was the last number over here on the end. Okay. Can you use synthetic division to divide this by this? The answer is no. So we're only using our synthetic division process when I have a first degree binomial that I'm dividing by. So here x squared plus 5, this is a second degree here. So no, I can't use my synthetic division. I could use long division, but I cannot use synthetic division. Okay, and that was it. Practice problems after that. I will see you tomorrow. Thanks.